I'm Colby Manwaring. I'm the Vice President of Innovyze at Autodesk. I've really built a career around water infrastructure software, operational analytics, and water infrastructure asset management.
Can you summarize the Scottish Canals project? What were the surface water problems that were affecting the proposed development? Why couldn't the canals be used without modification? And what would happen during a storm event?
Yeah, sure. So the canals around Glasgow, Scotland had essentially been left to rot. They weren't really being actively managed. They weren't being used in any real meaningful way. And as a consequence, the water quality in those canals had degraded significantly. I mean, they were a little bit like the rubbish bin. People would throw things in there. And as a consequence, the canals had become really a liability for the community. A little bit of a water quality problem, a bit of a hazard to the community as they were unregulated. And what would happen during storm events is there was frequently flooding from the canal. It essentially was the drainage feature for much of the surrounding areas. And as rivers, creeks do, right? When you get a big rainstorm, they would fill up and overflow, inundating the neighborhoods and the surrounding open land. As a consequence, that land around the canals had never been used. You kind of just had to stay off of it, right? You can't build anything there. You didn't really want to go and use it as a park or anything else because of the frequent flooding events. So the project, the intention was to make the canals useful again and to protect the community from flooding and provide some amenities to the community through the management of the water flow in the canals.
What was the proposed solution and how is it unique?
So the proposed solution was that active control of the canal level would allow the canal to function as a buffer for large rainstorms, and it would also allow the water quality to be improved to where the community and wildlife could actually make use of the water. And the concept was that there was enough storage capacity in the canals to handle the vast majority of storms in Glasgow. But if the canals were left unregulated, that essentially meant they were just constantly at whatever level that nature dictated. And as such, if there was a large rainstorm, there was no capacity to absorb that. Conversely, if there had been little rain and the canals were very low, the water quality was terrible, and the recreational use of the canal was not possible. The challenge was, how do you control a canal in near real time so that it can absorb the rain appropriately? I mean, one option is to have some people standing out at the gates watching the sky all day, every day, and they can control the gates when they see a storm coming. Not very effective, right? Just not practical, not possible. So the solution proposed was to create a digital twin of the canal where software analytics could be used to predict what was going to happen next in terms of rainfall and runoff, and then automatically control the gates on the canal to lower the level of the canal where extra capacity was needed to absorb a storm, or to maintain the gates closed to maintain the level of the canal high enough to preserve navigation as well as water quality objectives. So the whole concept was to digitize the control of the canals and create an automated system that was constantly watching and ready to react.
How are sensors and other on-site technologies used, and how are they monitored and used to create a better solution?
So there were a number, I think somewhere around the high 20s, maybe just under 30 water level sensors placed in the canal. What that did was allow knowledge of the depth, the level of the canal all the time, every 5 minutes. Right? Data would be sent from this sensor back to the software system, the digital twin, and thus knowing the level of the canal all the time provided a baseline for reaction depending on what was coming next. The other set of sensors are really, these are weather sensors. Of course, there's a great amount of technology in predicting rainfall and analyzing that. The weather sensors, the actual physical sensors, also were connected that would provide the actual rainfall. As we all know, there's often a bit of a difference between forecasted rainfall and what actually happens. So both sets of data, again, were linked through a SCADA system. So a SCADA system is a supervisory control system that essentially allows remote sensors to send all their data back to a database. With our software, ICM Live, connected to that database, we had situational awareness of what the canal level was, and we had forecasts of what rainfall could be, as well as actual rainfall data, all being fed in continuously to the system. So the sensors, they're absolutely critical to know what is actually happening out in the world. But of course, that's only half the story. Knowing what's happening and what rainfall is coming, it gives us a baseline, but the real key is connecting that sensor data to predictive simulations or predictive models that would take that data and convert it to prescriptive action. So if the rainfall forecast was for an extreme storm, then converting the expected rainfall into an expected amount of water that the canal would need to absorb would allow, for proactive management of that canal. So that's how the sensors play into it, is we need to know what's happening in real time or near real time out in that environment. Those sensors, again, those were installed over a period, and they're functioning and sending back data all the time.
How does the real-time control work within the ICM Live system?
So the ICM Live system pulls in the expected rainfall, the rainfall forecast, and uses a computational model to predict how much water do we expect to run off into the canal. Those are computational hydrologic methods that have been developed over many years, many decades. They're fairly well known, but the ability to pull that data in and run the model to get the forecast without any intervention from any operator is key, right? It's continuously predicting the volume of water that would go to the canal. The operating rules then dictate that if the volume of water that is predicted by ICM Live exceeds the current capacity of the canal, and we know the capacity of the canal because we know the water levels in the canal from the sensors. If it exceeds that capacity, then the ICM Live system sends a signal to say, you've got to open the sluice gates at the downstream end of the canal to let water out. And it's going to keep those gates open until the canal drops to where it can now absorb 80% of the expected volume. 80, why not 100%? Well, again, we all know that forecast of rainfall and reality of rainfall is not exactly the same. So the 80% mark allows a bit of a buffer to ensure that there wouldn't be flooding, but also we're not likely to impact navigation or water quality by letting the canal drop too far. So overall, the sequence is get a rainfall forecast, run a predictive model, open the gates for a certain duration to set the canal level to be ready to absorb the storm.
How often does the system modify itself? And what happens if forecasts turn out to be very wrong in either direction? How quickly can the system adapt and avoid problems?
So the first thing to know about the system is, as with many canals, it's not a rapid response system, right? The canal section that we're talking about, if the gates were fully opened, it would take at least 18 hours to drain it. And as such, when we're doing the analysis and the automated control, that's done every 3 hours. And so a set point or an operational decision is made every 3 hours to allow for the time necessary for rain to fall and start running off and see what the reaction is, and to not have the canal getting deeper and getting shallower really often, because of course that's a little bit unsettling to the community as well if it's constantly changing. So it's every 3 hours, and that response time and what I just mentioned earlier, which is the system is set to absorb 80% of a storm, allows that buffer between the forecast and the reality to be absorbed. If it rains a lot more, and we have the capacity to let that canal get deeper and deeper, there's multiple tens of hours to watch that happen, and then of course the system can just open the gates more and let more water out more quickly while that's going on. Conversely, if there's less rainfall than anticipated, it's going to switch the other way and say, whoa, close the gates now because we don't want to drain it down any further. So again, in about an 18-hour response time, if we are checking and recalibrating every 3 hours, we have 6 opportunities to adjust as that storm comes along. And ultimately, the canal doesn't get too empty and it doesn't get too full.
What can other water engineers learn from this project? How can it relate to other geographies and water conditions, even those that are vastly different?
Well, the first principle that can be applied everywhere is using real-time, actual data from the world to feed into analytical models. All right, the practice often has been to use theoretical data, design storms, or maybe past storms to design and build water infrastructure. What everyone can do now is operate that infrastructure in direct accordance with what is actually happening in the sky and across the land. So whether it's a canal or a storm sewer system in a typical city, or a water treatment plant that gets its water from the river, right? All of those things can be optimized. Right? The operation of those things can be optimized by using these live modeling tools and computing kind of what's going to happen next with a prescriptive action about what to do about it. That's a pretty substantial difference between years past, where you took your best guess at what would happen, you designed and built a system, and you hoped it handled all situations. Invariably, you come across a condition that was not anticipated and it doesn't handle. Here we can know that's coming in more real time and change the operations of infrastructure to be more resilient. I think the bottom line is we can make our infrastructure more resilient without having to rebuild it by using operational controls and real-time hydraulic models.
Is there anything else about this project that water engineers can learn from?
Well, I think there's an important point about the collaboration between the owners of the canal, right, Scottish Canals, who had a vision to reinvigorate the use of the infrastructure that they owned and maintained. The engineering consultant, which in this case was AECOM, who did a lot of the implementation in model building, in calibrating that model, and of course Autodesk, that was the technology and the software provider. Right? It is important to collaborate in infrastructure with owners and operators, technologists, as well as those practical hands-on engineers who have some experience in seeing how that system has operated. So it's not a matter of opening a piece of software and clicking go. There's an implementation process that is important for multiple parties to collaborate on. It's one of the big things that Autodesk we're working on is better collaboration across multiple parties, owners, engineers, technologists, so that all of that smart, all that intelligence from those smart people can be brought to bear on a problem like these canals.
We're here at Autodesk University. Are there any new news or information that you'd like to share with us?
Yeah, so continuing on this line of thinking of operational optimization, like Scottish Canals, we are releasing a product called Info 360 Plant, which is aimed at operational optimization of water treatment plants. Water treatment plants, it's almost the same story as these canals, right? The water treatment plant needs to know how much water is coming in and what the quality of that water is. And then the operations can be optimized to minimize cost or to minimize energy consumption and or maximize quality coming out of the plant, so that if it's drinking water, you and I are safe and can drink it safely. If it's wastewater, that water can be discharged to the environment safely. The Info 360 Plant software, much like the ICM Live software that was used in this project, pulls real-time data from the treatment plant, very quickly analyzes and provides prescriptive actions to be taken to optimize that plant. So in this canals project is a big outdoors flood mitigation and amenity project. Treatment plants are doing that all day, every day, and so this new software is aimed really at the treatment plant side, which I think is hugely exciting because everywhere in the world has a treatment plant. So every community can benefit from the Info 360 Plant release.